Okay, good. Now I can share my screen. All right. Okay. All right. So I thought what I would do is what we could do is we could start out with the foundational material. Let me tell you a little bit about myself. So I'm a professor at Baylor University in Waco, Texas. I graduated in 2007 from the University of Georgia with a field in with fields in econometrics, industrial organization, public and labor economics. I knew that I was going to be an empiricist, so I made econometrics my main field. Took me several attempts to pass. I wasn't the strongest student for sure. And since graduating, I've focused on topics in crime and risky sex. That research includes sex work, drug policy, abortion, and mental health care. And but we weren't taught causal inference in my courses, and so I had to kind of learn this material that I'm going to talk about on my own. And it just it's something that I accumulated from reading lots of different material, and I want to kind of put you together my synthesis of this material. All right, so I want you to imagine that there are aliens or extraterrestrials or spacemen that come from another planet, and they come to the planet Earth. And when they're at the planet Earth, they see our hospitals filled with people with COVID. And they conclude that these hospitals are hurting people because the hospitals are correlated with illness. They think that because it's correlated with illness, that it must be the hospitals that are harming the patients. So what they decide to do is they decide to release all of the sick people. They release them, and by killing all the doctors and killing all the staff. And as you can imagine, it doesn't work. It doesn't end up helping the patients. In fact, it ends up making them even sicker. And it sounds absurd when you hear it said that way. It sounds silly that somebody would make that kind of mistake, but we actually make that kind of mistake all the time. We just can recognize it as a mistake right now because we know how hospitals work. And because we know how hospitals work, when you present a correlation between illness and hospital, you can recognize the direction of the causality. But when you don't know how something works, you can't really use your prior knowledge to inform whether or not the correlation you're observing is causal or not. And so I want to look at some of the challenges before we start. I want to just look at some of the challenges that you face in research and as well as policymaking and in life in general that make it hard, that can be mistakes of confusing correlation with causality. So the first thing I want to say is that causal questions are very different from correlational questions. A causal question is goes like this: if a doctor was to place a patient on a ventilator, will her COVID symptoms improve? That's a causal question. Put a patient on a ventilator, change their sickness. Versus a correlational question. A correlational question is a statistical correlation. It's covariance between any two random variables scaled by their variances, the product of the square root of these two variances, and then you take the average. Okay, and that's what a correlation is, and even a regression coefficient looks very similar. Even a regression coefficient looks very similar, and these are not the same thing. This one is never brings up a correlational statistic, and this one doesn't have to be causal. So these are different concepts, and you want to keep them distinct in your mind. The second thing I want to point out is that just because something comes first doesn't make it causal. Just because something comes first doesn't make it causal. So every morning the rooster crows, all right? Every morning the rooster crows, and then the sun rises. So rooster crows, the sun rises. The rooster came first before the sun, but the rooster didn't cause the sun to rise. In fact, the sun caused the rooster to crow. That caused the rooster to crow herself. And you know, if you only make a sequence of events your concept of causality, then that will also lead to possible errors. There's a phrase in Latin. It goes posthoc ergo propter hoc, and it means after this, therefore because of this. And that's a logical fallacy. Just because something happened after something else doesn't mean that the first thing caused it. So that's another thing to avoid. But this one is a little bit more, even more strange. Sometimes two things won't be correlated and there will be a causal relationship. Okay, so this is a sailor piloting her sailboat across a windy lake. All right, and sometimes the wind blows and she, you know, pushes she moves the rudder this way, and sometimes she moves it this way. Now imagine the wind is moving back and forth, and she's moving her rudder back and forth in such a way that it perfectly cancels the wind. Okay, and as she therefore pilots her boat, even though she's moving the rudder left and right, the boat is going in a straight line. Okay, and so now these same spacemen look down and they see her and they say, her rudder is broken, because look, every time she moves her rudder back and forth, she stays in a straight line. So therefore her rudder must be broken. But they're wrong. There's nothing wrong with the rudder. The rudder is working just fine. There is no correlation between the rudder and the direction of the boat, but that's because she's perfectly changing the rudder. She's perfectly changing the rudder to offset the wind. And so sometimes two things will not be correlated, and in fact there's a causal relationship between those two things, which means that we're not going to be able to simply rely on regressions, OLS regressions, or anything even more sophisticated. We're not going to be able to rely on that naively. We're going to have to go further. We're going to have a new vocabulary for causality. And without that vocabulary for causality, we won't be able to make progress on these questions, because the correlations can be so misleading. All right. So here's going to be the vocabulary that we're primarily going to use. The vocabulary that we're primarily going to use is called the potential outcomes model. It was developed by Jerzy Neiman in 1923 or 1925. It was popularized in the physical sciences with the rise of the experiment. but it never really caught on exactly in economics. You saw a little bit of activity with this model with some economists, but they didn't necessarily build out this flexible notation. And so we're going to talk about it in terms of this flexible notation, because this notation helps clarify these questions of causality really clearly. So we're going to have a treatment variable called D, all right? And it's going to equal 1 if the person I, is in a hospital, and it's going to be a 0 if they're not in the hospital at the same point in time, all right? So I want you to imagine that this is John at, right at 12 o'clock noon, and he is either in the hospital or not. Okay, so he's either in the hospital or not at the hospital at 12 o'clock. All right, that's what we mean by that's what we mean by what we're talking about. We're saying John is hospitalized at the same point in time. Either he's in the hospital or he's not in the hospital. Okay. Now, obviously, you can't be simultaneously in the hospital or not in the hospital. All right. But we're going to pretend that you can at least be in one or the other. So there's one situation where John is in the hospital. And when John is in the hospital, we observe his health. Okay. So this becomes Y1 is John's health had John been admitted to the hospital right now at noon. Okay, so that's the first one. And Y0 is John's health had John not been admitted to the hospital right now. We call these different states of the world potential outcomes. They represent an outcome that could have happened, not outcomes that did happen. Okay, so it's that did happen. So it is a little different. It is a little different than the way we normally think. Okay. So I'm going to drop the T subscript, and I'm just going to say that a potential outcome is not the historical outcome. John is currently not in the hospital. All right. So John is not in the hospital. We do not therefore observe Y1 for John. We observe it for other people, but not for John. All right. For John, hospital is counterfactual. Means it didn't occur. Means it didn't occur. Even though it could have. Okay, even though it could have. So potential outcomes are hypothetical states of the world. They become real when certain things happen. All right. They become real when certain things happen. But before those things happen, they're just possibilities. They're just possible worlds that we could be living in. All right. Oops. Okay. So let me give you some definitions. Now, what we're going to say is the effect of hospitalization, right? The causal effect on John of hospitalization on his health is the difference between two potential outcomes. one where he is in the hospital, one where he is not. And so that is causal effect equals y1 minus y0. That is our basic building block of causality, of causal inference. That's our basic building block of causal inference. All right. So we've got here this individual treatment effect. All right. It's the difference between two states of the world. You could do this for an entire group of people. There's 50 people on the call. We could do it for the entire number of people on the call. We would just need to know everyone's Y1 on the call. No one on the call is in the hospital. So we only observe Y0 for the people on the call, but Y1 represents what could have happened. That's what represents what could have happened. So we have here the average causal effect, or what's called the average treatment effect, ATE, is the difference between the average Y1 and the average Y0, right? But you still do it. But this here, this ATE is still based on counterfactuals, because even though we have 50 people on the call, and even though we have all of their Y0 values, that's health in a world where they are not in the hospital. We do not have anyone's Y1 values. We don't know anyone's health had they gone to the hospital, and therefore can't calculate expectation Y1. Expectation Y1 represents the average. This is basically the population average of everybody's health in a world where they were in the hospital. And this is everybody's health on average in a world where they didn't. And if you could just take averages of both of these, well, then you could estimate, or you could actually numerically calculate. You wouldn't even be estimating. You would just be measuring the average treatment effect. Now, people have hypothetically, Y1 or Y0. John could have gone to the hospital this morning. It might have been, he could have presented himself to an emergency room, and they would have had to have admitted him. So we could have observed his health had he gone to the hospital. All right, and that would be Y1. But we didn't. We observed this one. So why did we observe John's Y0 and not his Y1? Okay. If they were both possible, then what determined which one that happened? And the answer is the treatment assignment. The potential outcome that occurs is a result of whichever treatment you've been assigned. So we observe your Y1 if you had gone to the hospital. It's that simple. Okay. But mathematically, we use definition 3 to make that to make that happen. Okay. So definition 3 says, I'll observe my real outcome depending on my treatment assignment. Now notice, if you had gone to the hospital, then that would be a 1. This would be a 0. All right. So I'll do it right like this. If you had gone to the hospital, that would be a 1. This would cancel out. 1 minus 1 is a 0. That would cancel out. And y would equal y1. If you had not gone to the hospital, d would be a 0. That would be a 0. This would be 1 minus 0. And so this would just become y0. So what we use to move, we use definition 3 to move between potential outcomes and reality. Your data is reality. Everybody's data in their data set is an outcome that occurred as a result of definition 3, right? Your data is real, and real data are not potential outcomes. They are actual outcomes. And that is a problem because definitions 1 and 2 are based on potential outcomes, not real outcomes. So this creates a problem for us. And let me show you the problem. The problem is if you have to know both y1 and y0 in order to say something causal, then you can't say something causal, okay? If you have to know both y1 and y0 to know if something is causal, but you only observe one of them because of definition 3, then you won't know it was causal. This is the challenge created by this definition of causality. If causality concepts are based on counterfactuals, then we face a major problem, which is we don't have counterfactuals. Our data is always missing counterfactuals. So how will we engage in causal inference without counterfactuals we need for causal inference? That is the point of this workshop. That is the point of this workshop. This workshop will introduce you to the scientific methods that humans have discovered, which can, under assumptions, reveal estimated causal effects. Estimated causal effects, okay? And we'll start with our first one. Before we get into those, I want to show you a couple of more definitions. These will show up a lot in the book. At least this one will. This one we sort of allude to, but this one will show up a lot. It's called the average treated on the treated. It's called the average treatment effect for the treated. In our example, the ATT would be the average treatment effect for people and for anyone and everyone in the hospital. Okay. Now, that would mean it is not the average effect for us because we are not in the hospital. All right. It's the average effect for those in the hospital, not out. All right. So you say it like this. This is the treatment effect. right here, delta, 4 people in the hospital. All right, so we put in the definition of treatment effect here, expectation Y1 minus Y0 for the treatment group. And then we distribute these terms and we get expectation Y1 for the treatment group, expectation Y0 for the treatment group. All right, now notice this is observed. This is observed by definition 3. That is not observed. Not observed. You do not observe the health of sick people who are in the hospital had they not been in the hospital. This is counterfactual. This is counterfactual. This is historical. That's historical. So the ATT is missing counterfactuals based on not being in the treatment. All right, based on not being in the treatment. And then there's the ATU. Oops. There's the ATU. And the ATU right here, the ATU right here is the average treatment effect on the untreated. The average treatment effect on the untreated. And the average treatment effect on the untreated is the effect of hospitalization for people that are not in the hospital. This would be the one that applies to us because we are the untreated, t equal 0. If we could access our counterfactual health in a world where we were in the hospital, then we could calculate our ATU. So causality and comparisons are ultimately, you can see here, every causal concept right here does involve comparisons. Look, we're comparing 2 states of the world. All right, we're just not comparing 2 different groups of people. Notice this. This is comparing states of the world for the same group of people. States of the world for the same group of people. States of the world for the same person. Okay, so causality always involves comparisons. It's just that its definition involves comparisons of for the same group of people. But we said right here that definition 4 says you can't get both of those pieces of data. You can't get data for John, his health in a world where he went to the hospital. All we have is his health in a world where he didn't go to the hospital, right? But if you need both of them, you can't make that comparison, okay, if you're missing one of them. So what humans do instead is they compare different people to each other, right? They take groups of people that are treated and they compare them with groups of people that are not treated. And they want to understand when they do that kind of comparison, well, will that reveal a causal effect or will that just reveal a correlation? Okay. So what I'm going to do is I'm going to walk us through what's called the simple difference in means outcome. All this is right here. The simple difference in means is just the difference between average health for people in the hospital and average health for people not in the hospital. It's all that it is. Nothing more, nothing less. Nothing more, nothing less. Okay. So what I want to do is decompose the simple difference in outcomes into whatever it is in terms of causality. Right? I'm going to look inside this estimator and understand its causal components and its biases. All right, so let's do that together. Let's do that together. All right, so what I'm going to show you is that simple difference in outcomes right here, which is the average health. It's the average health for people in the hospital minus average health for people not in the hospital. So notice the SDO is comparing different states of the world and different people. Okay, that makes it different. So the AT was the same people, different states of the world. The STO is different people and different states of the world. So these are subtly different estimators, or let me say it this way, comparisons. These are subtly different comparisons. All right, so we have this, and we get the average treatment effect. All right, so what I'm going to show you in a moment, next slides, I will show you how I got the information on the right-hand side of the equal sign. I will show you that, okay? But it will come out to the average treatment effect, this term, and this term. Now, what I'm going to do is I'm going to go in a series of steps. This is going to be one of the only times I work through the proofs. It's going to be one of the only times I work through the proofs. All right. So we've got here the average treatment effect. And the average treatment effect is going to be expectation Y1 minus expectation Y0. All right. So this is the definition of the average treatment effect. And then we're going to get, we're going to use the law of iterated expectations to write out the definition of each of these expectations as the weighted sum of several conditional expectations. So expectation Y1, all right, so I'll just kind of highlight this. Y1 is equal to this. Y0 is equal to this, okay? So look real closely. Now, pi is the share of the population in the treatment group. And in this equation, it is a weight. Okay, it is a weight. So we are using the law of iterated expectations to decompose the expected value of Y1 into its weighted averages, okay, to its weighted averages. So you see right here, expectation Y1, notice it's the weighted average of all values of y1 under different states of the world. So you've got here expectation y1, and it equals pi expectation y1 for the treatment group plus 1 minus pi expectation y1 for the control group. Y0, pi expectation y0 for the treatment group, 1 minus pi expectation y0 for the control group. So notice all we are doing is adding together all averages of y1 or y0 under various states of the world, and then weighting them to get the unconditional expectation. All right, that's all that we're doing. All right, so we're going to substitute letters for expectations. I'm going to here this one, I'm going to give it an A. This one, I'm going to give it a B. This one, I'm going to give it a C. And this one, I'm going to give it the D. All right. So I'm just making these substitutions. I'm going to leave these alone. These will stay in the expression. And then the last thing I'm going to do, is I'm going to take E. I'm going to replace ATE with the letter E. Then I'm going to rewrite it down here. So I get ATE, letter E, is equal to the sum of all these conditional expectations. That's all that it is. It's the sum of all these conditional expectations. So you've got here pi A. So notice here pi A. Remember we got the A in there. Pi A plus 1 minus pi B, 1 minus pi B, pi C, 1 minus pi D, 1 minus pi D. All right. So all we did was use LAE to get conditional expectations and weights to substitute letters for conditional expectations, rewrite the definition of ATE with letters and conditional expectations. That's all we did. Okay, that's all we did. So what I'm going to do now on the next slide is I'm going to manipulate. On the next slide, I will manipulate this equation to reveal what a simple difference in outcomes equals. All right, that's what I'm going to do. So lots of stuff on this page. Let's go slow. And I hope it's okay that I'm going slow through this. This is kind of the foundational material, and I want to make sure that as many of us as possible are understanding what I'm doing. Okay, so I rewrote it here. It's the same thing. Okay, and then all I'm going to do is I'm going to distribute these terms. Pi A plus B, there it is right there, minus pi B here, minus pi C plus D times a negative minus D plus 1 minus pi D. So this becomes minus pi D times a negative positive pi D. So all I did was I distributed the terms. Okay, I distributed the terms. Now what I'm going to do, I'm going to add zeros. to the equation. Now, when you add a 0 to an equation, you've not changed anything. So adding this 0 here, adding this 0 doesn't change anything. This is 0, a minus a, c minus c, d minus d. But I did it because I'm going to use these letters and I'm going to use these concepts, okay? So I added in these letters, all right? These are zeros, nothing changed. Now what I'm going to do is I'm going to move everything to the left. All right, I'm going to move everything over. And then I'm just going to put everything on the right that was on the left. All right, so notice what I get here. I get E minus pi A minus B plus pi B plus pi C minus D, or plus D minus pi D minus A plus A minus C plus C minus D plus D. Okay, so nothing's really changed. All that these steps are just rearranging. They're not even really algebra. All right. So now what I'm going to do, is I'm going to take this one and I'm going to move it here. Then I'm going to take this one. I'm going to also move it here. All right, I'm going to take those two letters and I'm going to move them to the left-hand side. I'm going to move them to the left-hand side. So now I get over here A minus D. A minus D is, I'm going to come back to that in a second, but all that I've got now is I've got this equality that by the definition of the average treatment effect, A minus D equals the average treatment effect plus all of these terms. All right. So that's the thing I want you to realize. All we've done is we took the definition. All we did was we took the definition of the AT. And then what we found is that this difference equals the AT plus additional material, right? Because look, here is the AT. So what is this? What is this term? All right, so look at A. What is A minus D? It is expectation Y1 for the treatment group minus expectation Y0 for the control group. All right, so look, A minus D is the simple difference in outcome. It's the average Y1 for the treatment group minus the average Y0 for the control group. Okay. Average differences in averages, average potential outcomes for different people. It's not the AT, it's something else, but it equals the AT plus additional factors. Because watch. The simple difference in outcomes equals the average treatment effect plus this additional stuff. Everything in blue is actually bias. It's biases. The letter E is the AT. It's what we care about. It's what we want to measure. The rest is bias. The rest is bias. So we get A minus D equals E plus C minus D plus this additional material. A minus D equals E plus C minus D plus I have all these 1 minus pi's. Then I group them together and I get A minus D equals E plus C minus D plus 1 minus pi, A minus C minus 1 minus pi, B minus D, right? So the 1 minus pi is the share of the population in the control group. So what is A minus C and what is A minus D, B minus D? What is A minus C here? What is B minus D? So let's look at that. Let's look at what that is. Okay, let's go back to the previous slide and let's see what A minus C and B minus D is. Okay, so this is A minus C. All right, so look at this. A minus C is the difference in average potential outcomes in different average potential outcomes for the same group to equal 1. Right? This is called the ATT because it is only referring to the D equal 1 group. All right. So we get expectation Y1 minus expectation Y0 for the same group of people. Okay. Versus B minus D. B minus D is the difference in the average potential outcomes for the control group. D equals 0. This is the ATU. This is the ATU. So what this means is the simple difference in outcomes has 3 parts. First, it's the average treatment effect. Second is this term, which I'll talk about in 1 second, this term. And then third is this term. So there is AT. There is this weighted difference between ATT and ATU. And then there's this part. What is this? What is this C minus D? Let's look at that again. Let's look at the C minus D. Okay, so this one's different. This is not a causal expression because it is not referring to 2 different potential outcomes. It is referring to 2 different groups of people. All right. C minus D is called selection bias. It is the difference in average Y0 for 2 different groups of people. Okay, so the group who is in the hospital and the group who is not. All right, so if you think people in the hospital were sicker before they got the hospital than healthy people, C minus D doesn't equal 0. Because look at what C minus D is. Expectation It's that. It's the difference for two different groups of people, potential outcomes in a world where they're not in the hospital, right? So notice Y0 is health, not in the hospital, but it's the average of that value of that variable. It's the average of that variable. It's the average of that variable for two different groups. One not in the hospital, one in the hospital. And if you think these two groups had different Y0s, then you have selection bias. And the simple difference in outcomes will not equal the AT. It will not equal the AT because it will be contaminating it. So we see right here, the simple difference in outcomes, which is this right here. This is just using sample average notation. These are just samples now because we don't observe, we use through definition 3, we replace Y1 for the treatment group with Y. And we replace Y0 for the control group with Y. So what we do is we replace those here. And this is the simple difference in outcomes. And this would just be a simple Excel calculation. It would just be something like, equal average for a group minus equal average for another group. All right. But what that number, this right here, Stata, R, or Python, or Excel will always calculate this number. It's just that this number won't necessarily be causal. It will always equal the values on the right. But sometimes some of those values will be 0. Okay, so look at what we get though. When we calculate the simple difference in outcomes, we get average treatment effect, and this is our target parameter right here. This is what we want to know. We usually want to know a causal parameter, and this is the one we want. But we can't get it because we have selection bias. All right, we have selection bias. So here is the selection bias, and here is this third source of bias, which we saw was just mathematically there. It is the difference in the returns to hospitalization for the hospitalized group and the non-hospitalized group, weighted by the share of the population that's in the control group. And I just call this the heterogeneous treatment effects bias. All right. So to conclude, the simple difference in outcomes reveals something. Even though it is not equal to the causal target parameter AT, it contains it. The target causal parameter AT is inside the simple difference in outcomes. So we can find it with the help of statistical models. Okay. But how? That's the workshop. All right. That's the workshop. The point of the workshop is to try to find situations where the selection bias or the heterogeneous treatment effects bias equals 0. That's the point of the workshop. Point of the workshop is to find how we can use statistical models to cancel out selection bias and heterogeneous treatment effect bias. That's what we're wanting to do, right? So the first one we will learn is how randomization does this. It'll be how randomization does this. We will examine why randomization works to isolate a causal effect. Okay, that's what we'll do. And we'll do that by introducing the independence assumption. All right. So let's imagine that the treatment, hospitalization, had been assigned to individual units for reasons that were independent of their potential outcomes. What would that mean? That would mean the treatment was random. Okay? Because you and I, independence is not natural. Okay? It is not natural. It really is something humans do for experimentation usually, but not always. When I go to the hospital, I do so because I believe y1 minus y0 is positive. I think my health will be better if I go to the hospital than if I don't. All right. That's what I think. I think my health would be better if I go to the hospital than if I don't. Likewise, if I don't go to the hospital, then it's because I believed y1 minus y0 was negative. I did not go to the hospital because I believed my health would be worse if I went to the hospital, or, at least wouldn't be better. All right. Both of those are based on rational choice, utility maximization, optimization. All right. They're both based on optimization. And utility maximization means that the treatment is not independent of the potential outcomes. You chose the treatment because of the potential outcomes. So independence likely does not describe your life, right? But if it happened, it would mean someone assigned a treatment to you, for reasons that had nothing to do with your potential outcomes. Okay, they assigned it to you randomly. They flipped a coin. They used randomization, not utility maximization, to assign the treatment. Okay. So in plain language, this notation right here, all right, this notation right here, Y0, Y1, independent, statistically independent of D, all right, means that the random assignment that has been made to people for reasons that have nothing to do with their potential outcomes. And this ensures what this does, independence is special because of the two equations that it creates at the bottom. First, average Y0 is now same for each group. Okay, under independence, the average Y0 is the same for each group, and the average Y1 is now same for each group under independence. Randomization causes the average potential outcomes to be the same for each group. Okay, that's all that it does. What it's doing is it's just ensuring that everything is the same about these two groups of people, hypothetically, even their potential outcomes are the same. All right. But when you actually go through the simple difference in outcomes, this is the simple difference in outcomes. When you have independence, it's going to directly affect these two things. So look, first one, independence yielded that equality. Okay, it yielded that equality. So that's this equality right here. Expectation Y0 for the treatment group minus expectation Y0 for the control group. Now we said independence causes these two things to be 0. Right here, they're going to be 0. So look, if that is implied by randomization, we see it right there. So the first thing you get, independence automatically deleted selection bias, because selection bias was 0 under independence. All right. What about this one? What does it do to this one? Right, so let's write out the definitions of ATT. Let's write out the definitions of the ATT. And the ATT is equal to expectation Y1 for the treatment group minus expectation Y0 for the treatment group. And ATU is equal to expectation Y1 for the control group minus expectation Y0 for the control group. Okay. So let's write these out, because remember, selection bias is just a weighted average of those differences. So let's look at those differences. All right, ATT minus ATU, it's going to be this minus this, because I like using these pictures, these colors. Okay, so there they are. All right, now look. These and these. Okay, so this is what we're going to look at. We're going to look at those two terms right there. Okay, so when we do this difference, we've got both these differences showing up but we also have these differences showing up, right? So expectation Y1 for the treatment group minus expectation Y1 for the control group. Well, under independence, independence implies both are 0. Okay. Expectation Y1 for the treatment group minus expectation Y1 for the control group. Under independence, those are the same, so that zeroes out. And then we get over here, expectation Y0 for the treatment group minus, or that was negative. That was actually, sorry. Okay, so you get negative expectation Y0 for the treatment group plus expectation Y0 for the control group. Cancels out. So if independence holds, if treatment is independent of potential outcomes, all right, if treatment is independent of potential outcomes, treatment is independent, meaning randomized, then even simple differences in outcomes will identify the target parameter, AT. Don't need anything fancy. Okay, don't need any kind of fancy statistical model beyond that, because even this simple difference in outcomes will eliminate the sources of the bias. Now, when we do this, there are some assumptions that we're necessarily maintaining. And these assumptions are called they're wrapped up in this acronym called the stable unit treatment value assumption, or SUTVA. Let's look at what SUTVA is. SUTVA is a bundle of assumptions, means that the treatment effects are stable across all units. So this is the treatment value or the treatment effect. The treatment value is stable across all units. It's an assumption. What does that mean exactly? What it means is that when we are calculating these treatment effects, these treatment effects are based on everyone getting the same treatment, homogeneous dose, and no externalities from the treatment, and only partial equilibrium. Let's look at each of them. So this is homogeneous dose. SUTVA requires that each unit receive the same treatment dosage. So if we're looking at COVID ventilators, SUTVA requires every patient receive the same brand of ventilator. Technically, everyone is getting the same treatment for this calculation. So the comparisons require homogeneous dosages, not homogeneous treatment effects, homogeneous doses. Okay, everybody's getting the same treatment. Secondly, no spillovers or no externalities. No externalities means if John is put on a ventilator, SUTVA requires that I don't get better just because he is on the ventilator. SUTVA prohibits externalities. Okay, SUTVA prohibits externalities for this calculation. You can estimate causal effects with externalities, but it won't be as simple as what we just showed. Okay, won't be as simple as what we just showed. And then we have partial equilibrium. Partial equilibrium. And the partial equilibrium basically means that we're not making calculations using the simple difference in outcomes, usually for general equilibrium. So I want you to imagine that Joe Biden is learns about a study that was done in where I live in Texas, does a study where we found that there was an early childhood intervention that improved the life outcomes of children. All right. And it was a randomized experiment in Texas. Okay. And President Biden says he wants the entire country to have it. Will it have the same effect for the entire country as what was found here? Now, scaling up a policy can be challenging if there are rising costs of production. If there's rising costs of production, then it can have challenges to scale it up. Because what if, to make it large, you have to hire lower quality teachers than was in the randomized experiment? Then you might not be able to do the same study. You may not be able to do the same study using, what you learned in Texas may not hold for the rest of the country, not because there was bias in the Texas study, but because the Texas study was only in partial equilibrium, not general equilibrium. So I want to talk you through a study by one of my best friends, Rebecca Thornton at the University of Illinois. Some of you may know her. She's a development economist, has historically been a development economist. And this was a project that she did in graduate school in Malawi. And this was a very influential study, as I understand. Rebecca's career early on had been in the area of HIV, largely in sub-Saharan Africa. So at the time, as I understand it, it was believed that you could address the HIV epidemic in Africa by encouraging testing. But Rebecca wanted to see if that was true. So what she did was she did a randomized experiment where she wanted to incentivize people to learn their HIV status. She then examined what the impact was of the incentives on sexual behavior. So the experiment was a free door-to-door HIV test. Respondents are being offered a free door-to-door HIV test. Treatment is randomized vouchers worth between $0 and $3. These vouchers were redeemable once they visited a nearby voluntary counseling and testing center. She estimates her models using OLS with controls. Okay, so respondents are going to be offered free tests. They're going to also be given vouchers worth anywhere between $0 and $3 to go to a voluntary counseling and testing center to learn the results of their test. Right now, everybody's getting tested, but not everybody's learning their test. They have to go get the results themselves. She's going to estimate her model with OLS, with and without controls. Now, to evaluate experimental data, you may want to add additional controls into a multivariate regression model. So instead of estimating the prior equation, we might estimate this equation. Yi regressed onto a constant, a treatment dummy, and maybe some covariates. Now, you technically don't need to control for the covariates if you have true randomization, because true randomization will ensure that all of the covariates are equally distributed across the treatment and control group. But sometimes people will do experiments that aren't truly independent. They'll do some kind of conditional randomization. So maybe they'll choose schools and then randomize within the schools. Maybe they'll choose men and then they'll use some probability for men, but to get the treatment, but the probability you get the treatment for being a female is different. Okay. So maybe that's one thing, is you have conditional random assignment. But the second thing is, if you can pull things out of that error term, if you can pull them out of the error term, then you can reduce the residual variance, explaining the variance in Y due to the residuals. And so that's another reason to control for things. It can reduce your standard errors. So here is her table. Apologies, this is a bunch of numbers. So let me just kind of walk you through it. Let's look at this one. Now what she's going to do is she's going to take, even though the treatment is 0 USD to 3 USD, she will make the treatment any money. So that is 1, 2, or $3. So if you get $1, $2, or $3, you'll be in the treatment group. And if you get $0, you'll be in the control, right? So what Rebecca finds is if you are assigned to the treatment group, meaning that you received any money, there is a 43 percentage point increase in the probability that you will learn your HIV results. If you receive any money, there is 43.1 percentage point increase in learning your HIV status, right? So that's this one. So what's this one? Here, all she's doing is she's putting in nonlinearities. She's allowing for nonlinearities in the payment to affect the outcome. All right, so she's going to put in a dummy for whether or not the person was in the treatment group. And if they are in the treatment group, she's going to put in how much money they got. Okay, she's going to put in how much money they got. So if they're in the treatment group, it's going to increase the probability that they get that they learn their HIV status. It's going to increase the probability they learn their HIV status by 31 percentage points. And it's going to go up 9% for every additional dollar. Here, she's going to put in, sorry, this was linearities and this is the non-linearities. So she's going to put in the non-linearities. Now she's going to be the square term. So it's going to be each person is going to get, so if a person has gotten $1, then their square is $1. If they got $2, then their square is $4. And if they got $3, then their square is $9. So she's putting in these non-linearities. And notice what you see. Each additional dollar increases the probability of people learning their HIV status, but at a decreasing rate. All right. And then we've got the random assignment. The other thing she did, this was an interesting study that Rebecca did. Rebecca also randomized their distance to the clinic. And what she finds is the further away that you live from the clinic, the less likely you are to go learn your HIV status, even conditional on how much money you've been paid. It's a really interesting study. So on the face of it, someone in African administration and policy might be excited at this point. Rebecca has confirmed one part of the broader belief that testing can be a powerful weapon in fighting the HIV epidemic, because if you pay someone a little amount, actually, if you pay someone any amount, they learn their HIV status. They learn their HIV status. Right? And this is a visualization of it. This is a visualization of it. If you got no money, if you got no HIV, if you got no voucher, then there's about a 33% of the people that got no incentive, 33% of the people that got no incentive learned their HIV results, and about 79 of the people that got any money learned their HIV results. So you can incentivize. So I think Rebecca shows you can pay people to get their results, and it can have a large impact on whether they, in fact, get their results. But when you learn your results, how does it change your behavior? So here's what she did. She estimates an instrumental variables model, which we'll talk about on Thursday, either Wednesday or Thursday. She estimates an instrumental variables model. Now, what do you do with an instrumental variables model? What she's going to do with this instrumental variables model, in this IV model, she will use the voucher, the randomized voucher, as an instrument for whether the person learned their HIV results and learned they were HIV positive, using an interaction of got results with I am HIV positive. Okay, here. So this right here, what this has done is essentially this specification is randomly learn you are HIV positive. That's all that it is. It's a randomized knowledge. It's randomizing the learning of HIV status. All right. So she has randomly assigned knowledge to her population. All right. And here's what she finds. She finds that they are more likely to buy a condom. Okay. They're more likely to buy a condom. Now, it's not statistically significant, but it's positive. So they're more likely to buy a condom, but they only buy 2 more condoms. Okay. They only buy 2 more condoms. So this part of her paper is not very encouraging to policymakers. Even though you can pay people to learn their HIV status, that does not, in her study, cause people's behavior to change very much. So for those who were HIV positive and got their test results, 42% were more likely to buy condoms, becomes insignificant. The number of condoms bought is very small. HIV positive respondents who learned their status bought only 2 more condoms. And Rebecca has told me that even that might have been influenced by some peer pressure at the voluntary counseling treatment and voluntary counseling treatment center. All right, so randomization inference and causal inference. We're going to talk now about a form of inference. So what with a quote by Susan Athey and Hito Embens? In randomization-based inference, uncertainty in estimates arises naturally from the random assignment of the treatments, rather than from hypothesized sampling from a large population. Athey and Embens are part of a growing trend of economists using randomization-based methods for doing causal inference, right? Now, I don't know why randomization inference has gotten more popular, but it has gotten more popular. It's grown in popularity over the last many years, at least 10, and I'm not sure why. Computers have gotten better, so that could be part of it. Could be because computers have gotten better. Could be because data sets have gotten larger and we're no longer working with samples of data. Oftentimes we're working with the universe of data. Those may sound like they shouldn't really matter. Why would those things matter? But as we'll show, both of those are kind of directly related to some of the assumptions behind the construction of, I guess, valid standard errors using traditional testing procedures, and randomization-based inference is kind of doesn't make the same assumptions that some of those other techniques do. So let's go to a the history of randomization inference. Let's go to who invented it. His name is Ronald Fisher. He was born in 1890, was a British statistician and geneticist. He's kind of, one of the fathers of modern statistics, maybe the most influential early statistician in the early 20th century. He wrote 2 classic books, Statistical Methods for Research Workers in 1925 and The Design of Experiments, 1935. He apparently also wrote a very famous book in genetics called The Genetical Theory of Natural Science. So that was kind of his body of work. And he also wrote numerous articles. I think he may have even been an editor at Biometrica. I could be wrong about that. He develops many fundamental ideas in modern statistics, including the theory of the randomized experimental design. Now, he does not come up with the potential outcomes notation. He is not responsible for that potential outcomes causal model. What he is responsible for is seeing the link between the potential outcomes model that his colleague invented and the need to physically randomize. He's actually the one that had the insight that we should physically randomize in our experiments. Not, that was him. That was Fisher. I'm not positive if the beginning of the randomized experiment happens, because I was speaking with a friend at the University of Illinois, and they have a large crop, like a large agricultural experiment that's been going on for like 200 years. And he told me that it has always been a randomized experiment. So, I don't exactly know how to reconcile that with what I understand to be true. But my understanding is that Fisher had the key insight that if you wanted to isolate causal effects, you needed to have randomization. Okay. Then there was a woman that he worked with named Muriel Bristol. She was a PhD scientist in the days when women were not PhD scientists. By all accounts, that she was a genius. She worked with Fisher at the Rothamsted Experiment Station. These were in England in 1919. And one day during afternoon tea, she claimed that she could tell the difference just from tasting tea. She could tell if that cup had applied the milk first or the milk last. She could tell. So she's saying, she's saying that, you have a cup. You have a cup of tea. Either it was milk then tea, or tea then milk. She says she can tell the difference. She says you can tell the difference. Nobody believed her. Everyone thought that was impossible. No, I think that is kind of understandable. It's, if you don't possess that ability, it seems impossible, and it's not even clear how that could even be possible, given it's a mixture. At least, kind of at a naive level, it seems like, whether you put the salt in before the water or the water before the salt, the mixture should taste the same. Should be the identical mixture. Now, maybe it has something to do with the heat. Maybe it's got, something like that is going on, but still, that's a very incredibly sophisticated palate. Fisher has an interesting response, though. He doesn't say that's ridiculous. He has this epiphany. He says, there's a test for this. I know a test that we could do that would tell us whether or not Muriel has the ability that she thinks she has. And he, at that moment, presents the test. I don't know if he'd been thinking about it. I don't even know if I'm getting some of the facts wrong, but everything that I'm saying, my understanding is that it's correct. So he devised a test, right? Now, here's the description of the experiment. It is technically, I guess, an experiment in the sense that he's going to present 8 cups of coffee to Muriel Bristol. Sorry, 8 cups of tea. 4 of them are going to be where the milk was applied first, and then the tea, then the hot water, then the tea, correct? And then the tea is going to come before the milk. All right. And then we're going to present each cup to Bristol for a taste test. So the question is, how many cups must Bristol correctly identify to convince us of her unusual ability to identify the order in which the milk was poured? All right. So Fisher Sharpnell is what we're going to talk about. Somebody said something in the chat. Okay, good. Yes. All right. So, and also, by the way, I will send to John not only the slot. So I posted the Dropbox link. Let me just do this real quick. I'm going to send this to John also, so that everybody has it by email. But this is the Dropbox link to this workshop here called CI Workshop. And there's a lot of material in here that I'm going to go over with you over the week. There's the slides. There's also a bunch of do files. It's called master do files. It's actually got R files as well as do files. And it's also got some additional material. So we will be able to kind of, today's stuff doesn't have any actual coding, a little bit in just a second, but the rest of the week will. All right. So, so the question is, here's the question. Having presented 4 of each to Mariel, Fisher wants to know how many must she correctly identify in order for us to know, well, no, sorry, in order for us to believe that she's got the talent that she claims that she has, right? How many ones must she get right? Does she have to get all of them right? Does she have to get most of them right? Does she have to get 7 out of 8 right? What exactly is required, for us to know? Because we can't observe that she has this talent. Can't observe that she has this talent. So what Fisher does is he says, assume that she can't tell the difference, right? So this is the nature, the philosophical approach to this test is to begin with a claim. Assume she doesn't have this talent, right? She's guessing. Then if she's guessing, how many guesses are consistent with guessing, and how many accurate guesses are consistent with her claim, and how many, actually that's not it. All right, so assume she doesn't have this talent. Then what Fisher's test will do is quantify the likelihood that she would get the correct answer by only guessing. That's all it's really going to be. All it's really going to be is it's going to say, I'm going to be able to quantify the probability. I'm going to be able to quantify the probability that she's guessing. I'm going to be able to quantify the probability that you would get the correct answer if all you were doing was guessing. You'll get the correct answer 5% of the time. You'll get it 50% of the time. That's all that we're going to do. Okay, we're just going to see what is the likelihood that random chance was responsible for her answers. And if it is sufficiently small, if random chance would produce the correct answer only 5% of the time, and she got the right answer, he's going to propose that we believe her under certain criteria. Okay, it's going to be basically that simple. Now, to answer this question is to answer a combinatorics problem. It's all about choosing, it's all about what it's going to do is it's going to basically calculate through a method that I'm going to show about all of the different outcomes under different subsetting of the data. And this calculation is going to be used to construct exact p-values. For some reason, I'm a little disoriented. I apologize if I'm not making a lot of sense. Hold on, let me drink this cup of coffee. So the lady is going to perform the experiment by selecting 4 cups. She's basically going to select the 4 cups that she said had the tea poured into it. So I think she knows that it's 4 cups. So she's going, so she knows it's 4 cups, my bad. So she's been told she's getting 8 cups, 4 of them have the correct tea, right? So that's the treatment assignment. She knows that 4 and only 4 have tea applied first, 4 have milk applied first. There are 8 choose 4 ways to choose 4 cups out of 8. All right. So the numerator, 8 times 7 times 6 times 5, there's 1,680 ways to choose first cup, a second cup, a third cup, a fourth cup. All right. So she can choose in any particular order, but there's 1,680 ways to make those 4 choices. That's the numerator. And the denominator are the 24 ways to order those 4 cups. Okay, so those are the two pieces of information that we have. We divide the number of ways to order the cups by the total number of ways to choose them, and we get 1/70. All right, so what that means is there are 70 different ways to choose 4 cups out of 8. Okay, so you could choose, let's say it's the first, let's say that it's the first 4 cups. Okay, it's the first 4 cups. And it's been organized a certain way. She could choose 1, 2, 3, 4. She could choose 4, 3, 2, 1. She could go 2, 1, 3, 4. She could go 3, 1, 2, 4. There's all these different scenarios. But that's for a given ordering of the data, right? Where all of it's contained in those first 4 cups. You could have done it where it was all contained at the back end. You could have it kind of dispersed. So you can see how complicated it gets. Fisher knows this. I can't imagine Fisher is thinking of this on the spot. I don't know. It seems impossible, but he was also a genius. So he organizes it and he says the probability that she would correctly identify all 4 cups is 24 out of 1,680, or 1 out of 70, which is a 1.4% chance that just through guessing, she would get it right. Okay. So let's write this down. So if Bristol correctly chooses the 4 cups, but she had been guessing, she would get that exact answer 1 time out of every 100 guessing trials that she was engaged in. So it's quite a coincidence, in other words, that the 1 time we run this experiment, she gets it right. Fisher says this is an exact p-value of 0.0104. Okay, 014. It's called exact because it is based on an exhaustive thought experiment of the treatment assignment being artificially assigned. It's hard to see it exactly in this original example because it's a strange experiment, right? It's a strange experiment. He's not estimating, for instance, causal effects. He's trying to deduce the likelihood she can do what she thinks she can do. So it's expressed strangely to us who are used to thinking about experiments in terms of estimating causal effects. But the idea is the same. So let's now look at this same idea in an actual RCT. Okay, let's look at the same idea in an actual RCT. What does this exact p-value mean in a traditional RCT? Why is it useful? And how does it differ from more traditional hypothesis testing? Okay, so that's what we're going to look at now. So randomization inference allows us to make probability calculations. Okay, you're using randomization inference to basically construct p-values. Right, so that's the thing you want to keep in mind. We are using randomization inference in order to get p-values. Okay, this is not the first time you've ever heard of a p-value. So just keep that idea of a p-value in mind as you're thinking about this. We're trying to figure out the likelihood that this will be determined by chance. Randomization inference is going to allow us to make probability calculations, revealing whether the treatment assignment was unusual. All right, unusual. All right, so it's going to be a specific way of making that judgment about whether it's unusual. Now, Fisher-Sharp null is when we entertain the possibility. This is kind of the key part of the Fisher-Sharp null. Fisher-Sharp null. Fisher-Sharp null is another name for randomization inference. It's also sometimes called permutation inference. Okay. And in all of these, you imagine that there is actually no treatment effect. There's just nothing happening as a result of the assignment. Okay. But what Fisher showed is that this assumption that nothing is happening is actually a very useful assumption, because it will make certain implications in the data that we can check. All right. So we use this assumption of no treatment effects, or for Bristol, no ability to tell the difference between cups of tea. We use this assumption to calculate exact p-values using a particular multi-step method that I will show in a second, right? But what we're going to do is we're going to use this method to construct not like asymptotic p-values based on some sort of the p-values that we construct are exact, not approximate. They are not going to be based on some assumption about the error terms distribution. It won't have any parametric assumptions like that. It will be based purely on a combinatorics solution. All right, not a belief about the distribution of errors. Okay, so before we go any further, there's lots of different, before we go any further, there's actually several alternatives to, calculating probability statistics associated with comparisons, besides randomization inference, Fisher-Sharp null, and using statements about sampling distributions. Okay, so you've got other ways. For instance, you have the bootstrap. Is randomization inference similar to the bootstrap? Yes and no. They are similar, but it's really the ways that they are different that is most important. Okay, so sometimes people will confuse. We had a job market candidate. We had a job market candidate come to my university and present a paper doing bootstrapping and calling it randomization inference. And so I think that sometimes there is some slight confusion out there about how these are different from one another. And let me just show you real quick what it is. So so you have here bootstrapping. And you have over here randomization inference. Well, let's say that we have a database. I'm just going to kind of draw a database with a square. All right. It's going to have like this square. So this is like, you know, I 1, 2, 3, 4, ... n. And this is K 1, 2, 3, 4, ... K. All right. So these are variables. And these are people. All right. So this is like race, marital status, income, right? And so randomization inference, bootstrapping, what bootstrapping does is you randomly sample from the data a new data set, and then you do your analysis on the smaller data set. And then number 3, you repeat that thousands of times. So you would do something like this. You would say, okay, pull this one, this one, this observation. You're just kind of pulling out people, right? Well, actually, it would be more like this, right? So you would pull like this one, this one, this one, this one. You know, you'd pull like 10%. You'd get, you know, just this, you know, but you wouldn't get, you know, you wouldn't get this one, you wouldn't get this one, you wouldn't get this one, you know, and you would do your analysis off just those observations. Then you do it again. Okay, and you do it over and over. So that was like, that's trial 1, trial 2, trial 3, and you get this over and over. And then, you know, you can do, you know, various kinds of hypothesis tests based on like, you know, so maybe these are all the coefficients on a regression. Here's like a 0. And you could sort of see how the coefficients from each of those samples differ from each other. That's bootstrapping. Okay. Versus randomization inference. Randomization inference, oops. It's going to be the same thing. I equal 1, 2, 3, n. And what you're going to have here too is you're going to have all these k equal 1, 2, k, but you're also going to have this right here, a dummy variable equaling the treatment status, and it's going to go 1. Okay, you're going to have all of this, you know, all of these varying values. You're going to calculate some statistic using D, and we'll have here Y. You know, so this is like some outcome using D and Y. You're going to calculate some statistic using D and Y, and then you'll conduct the randomization inference. And what the randomization inference is going to be is it's going to be this pretend experiment where you use your exact same data, but now pretend that they had been assigned to a different treatment group. So you're going to calculate some statistic, then you're going to randomly assign You're going to randomly assign D artificially in your data. And you're going to do that over and over again. So this one over here uses subsets of the data, randomly sampling from the, whoops. Okay. So if it's like n equal 1,000, oops. So if it's like n equal 1,000, if it's like n equal 1,000, you might sample only 100. But with randomization inference, you're not working with samples. You're working with randomized treatment assignments. All right. So bootstrapping randomly samples observations. Randomization inference randomly assigns the treatment let's see, pretends to randomly assign the treatment. So bootstrapping for n equal 1,000 might use only n equal 100 for analysis. Randomization inference will always use n equal 1,000 for analysis, right? So one is uncertainty over the sample. One of them is bootstrapping randomly samples a percent of the total observations, uncertainty over the sample. Randomization inference randomly reassigns the treatment. It's uncertainty over the treatment assignment. I think Jason Kerwin at, I think Jason's at Minnesota, for helping me frame it so succinctly like that. So the following is from Hito Imbens and Don Rubin's textbook on causal inference, as well as Matthew Blackwell's helpful lectures. What we're going to do here is we're going to, again, like we said, choose a sharp null, right? So that's what this first step is called. The first step of every every form of hypothesis testing is to assume some null hypothesis. But for randomization inference, it's called choosing a sharp null hypothesis. Why is it called sharp? It's called sharp because we will be assuming something that is the same for all units. It's the same for all units, right? So we aren't assuming some average null. We are assuming some unit specific null. We're assuming some unit specific null, okay? And that sharp null traditionally here is going to be that no unit in the sample is ever affected by which treatment group they're in, because by assumption, the treatment doesn't work. So the sharp null assumption is the treatment doesn't work for anyone. It is a very strong null, stronger than the ones we usually use. Because the ones we usually use are based on means, not individual level. Right? So it's a subtle difference. And this was actually a source of conflict between Fisher and one of his colleagues. And most of modern statistics, the hypothesis test comes from the colleague named Jerzy Neiman, but more recently, Fisher's at least beginning to show up in economics. All right. So we're going to choose the sharp null. We're going to calculate some statistic. It's called a test statistic. All it is a number, a scalar based on D and Y. What is that? What might this test statistic be? It could be the beta coefficient from a regression. It's just any number based on comparing units in the treatment group and control associated with their outcomes. That's all that it is. Okay. So we're going to have here, choose a test statistic. Then we're going to pick a randomized treatment vector. We're going to pick a randomized treatment vector. And that's like the beginning of the new steps of the randomization inference. It's going to be a little bit easier, I think, to explain this one with an example, because I find that people who encounter randomization inference for the first time, this almost feels very abstract. So let me just kind of summarize it. So we're going to pick a randomized treatment vector, D squiggle, D tilde. We're going to calculate, we're going to repeat step 2. We're going to repeat this steps 2 and 3, 3 and 4 over and over and over again after we have done every single treatment assignment possible. And at the last step, we'll calculate p-values. All right, so let me show you how we do it. Let's say that we've got some mental health intervention. There's an intervention for people that struggle with substance abuse and mental illness called dialectical behavioral therapy. It's been found to be very effective for certain kinds of mental illness and certain forms of substance abuse that's associated with that mental illness. And so we're going to do an experiment. We're going to take 8 people who are homeless, and we're going to assign a treatment, the dialectical behavioral therapy intervention, to this homeless population. In the United States, I don't know how it is in Africa, but in the United States, we have a large, we have 350 million people, and some small percent of them have mental illnesses, and some small percent of those people with mental illnesses end up homeless. By and large, our homelessness problem is mental illness related, and the way that mental illness interacts with work for the most part, and crime. And so we're going to pretend that this DBT intervention has been assigned to these 8 people. And what we're going to do is we're going to do like Rebecca did. We're going to pay people $15 to enroll in this DBT program. And then if they're enrolled in the DBT program, we're going to take measures of their mental health. So we're going to do some sort of survey, or we're going to evaluate them. And higher scores are going to be associated with improvements in mental health symptoms. All right. And this is the data that we get. Okay. So we get, Andy, he's been assigned to the treatment group, and I observe his health score. Ben, assigned to the treatment group, I observe his health score. Edith, assigned to the control group, I observe her health score. Frank, assigned to the control group, I observe his health score. All right. Now I've put over here potential outcomes. Now notice here, Y is the actual outcome that we discussed an hour ago. Okay. It is, though, based on definition 3 that we discussed. Y equal dy1 plus 1 minus dy0. So if you know D and Y, you actually also know either y1 or y0, but not both. Think about the sharp null that we chose. We chose a sharp null that said there are no treatment effects for any unit, none. What does that imply? Treatment effect equals y1 minus y0. And if there is no treatment effect, then y1 minus y0 equals 0, which means that should be a 10. Means that should be a 5. Means that should be 16. Means that should be 3. Means that should be 5. Means that should be 7. Means that should be 8. Means that should be 10. Fisher's sharp null of no unit level treatment effect gives us permission to fill in the missing data, because no unit level treatment effect means the potential outcomes are the same under both states of the world. And if they are the same, then we know the missing counterfactuals. They will equal the same value as the observed potential outcome. So this is the power of assuming the sharp null. It allows us to fill in missing data. But what does the ability to fill in missing data do for us? That's what we look at next. Okay, that's what we look at next. So Fisher sharp null has this expression. Fisher sharp null has that expression. Assuming no effect means any test statistic is due to chance. Think about that. Okay. So let's say we ran a regression of y onto d, and we find a coefficient of 5. Under Fisher's sharp null, that 5 cannot represent the AT, because under Fisher's sharp null, every unit has a treatment effect of 0. So the average must be 0. Therefore, the 5 from a regression must just be chance. Okay. Right. So assuming no effect means any test statistic is due to chance. That's all that it means. Any test statistic is due to chance. Fisher and this guy Neiman that I mentioned, I think I said his name, but his colleague, Fisher's colleague, was this guy named Jerzy Neiman. He's actually Neiman is the one that invented the potential outcomes notation. Neiman is the one that invented this way of representing causality with potential outcomes. That comes from Jerzy Neiman. Jerzy Neiman also developed various hypothesis testing based on different nulls, not the unit level treatment effect. They used to get into big fights. They didn't like each other. Interestingly enough, these men did not like each other. My understanding is that Ronald Fisher was not a very nice man. Jerzy Neiman kind of was a gentleman, and Fisher was not usually very kind to Neiman. And they had a lot of arguments that, kind of colored by that, colored by his personality. But putting that aside, Neiman and Fisher's test statistics were different. Fisher's was sharp and exact. Neiman's was not. All right. So Neiman's null was no average treatment effect, and Fisher's was the sharp, which was no unit level treatment effect. All right, so we're going to fill it in, step one, by assuming the sharp null. We can fill in those missing counterfactuals for our treatment group and those missing counterfactuals for our control group. And now we have a new data set. We have a new data set. It's actually a little more complete than the one we started with, because we can fill in some missing values using a kind of plug-in principle based on that Fisher sharp null in step one, right? So that's the thing we're doing here. Now I said that is going to help us. What is that going to do? Second step, calculate a test statistic. All right. Now that test statistic, okay, somebody's got a test. Angelica, yes, these lectures are in my book. This is all from my book. This is in, and the book, by the way, is here. The potential outcomes material, section 411, and Fisher sharp null comes in here, randomization section 4.2. So all of this has Stata code, R code, Python code, so that you can kind of reproduce some of this material. So, you know, the lady tasting tea experiment, there's code that will do it here. And it's all under this mixtape.scunning.com. So if you just go to mixtapescunning.com, you can find it. It's all right here. Okay, so a test statistic, all that a test statistic is really nothing more than some measurable correlation between D and Y, but between, how would I say this? Correlation. It's some measurable correlation based on D and Y, right? It's got to be a number though. It has to be a number. Scalar. Okay, can't be an equation, can't be a function. Has to be a test statistics. Test statistics in the Fisher sharp null tests are numbers. But regression coefficients are numbers, as is the simple difference in outcomes. All right. So we're going to have a lot of tests to choose from, and I'm going to review several. But if you want a test statistic with high statistical power, meaning that you have the ability to reject your null, right? If you want a test statistic with high statistical power, the test statistic that has the ability to be discerned from noise, all right? You need it to be large when the null is false, and you need it to be small when the null is true. All right, so that's what we're going to need. So we're going to make choices. You typically make choices about which estimator you use for step 2 based on the distribution of the data itself. Some distributions are such that very simple estimators are fine, and some distributions require a little bit of a different choice. But the steps 1 to 6 are the same. It's just that step 2 might use a regression, might use a log transformation, might use simple difference in outcomes based on the distribution of y, across the sample. Okay, so what I'm gonna do is most of this lecture will be, 1, showing you how the Fisher-Sharp null test works in practice, but also 2, showing you different test statistics for step 3. For step 2. That's really what we're going to do. And then also show you code that will do it. All right. So here is a simple. Here's one of the simplest test statistics you could ever calculate. The difference in average outcomes for 2 groups. Now, in this one, here we will take the absolute value, but you don't have to. Taking the absolute value makes it a little easier for calculating p-values. But really, all this is average outcome for treatment group, average outcome for control, difference, the averages. That third step, difference, the averages, is the test statistic for step 2. Okay, kind of going slow, mainly because I just want to make sure that everyone is following. So I apologize for anybody that this is too slow. I just want to make sure I'm not losing anyone, because I know I have a very thick American accent from the southern part of the United States, and that can be really challenging for people not from that can be really hard to understand. And I apologize that my accent is so thick, but I'm trying to go as slow as possible and use as much writing as I can. I hope that's okay. So it's a good estimator. So what you're looking for is large relative values. Okay, so what you're wanting is this number that you get, maybe it's a 5. Okay, so maybe when you calculated this SDO, you get a 5, right? Now, we don't know what this 5 means yet for randomization inference until we do steps 3 to 6. But for now, we have a 5. And what we need is, if we want to know whether this is likely a consequence of chance, we need for a 5 to be relatively large compared to whatever we find in steps 3 to 5. That's the key. The key is to reject the null, 5 must be relatively large compared to the test statistics we will calculate when we conduct steps 3 to 5, right? And that's what we're going to call evidence against the sharp null, will be because 5 is large. So larger values means relative to the test statistics we generate under steps 3 to 5. Okay, so what Embens and Rubin say is that this is a good estimator. This is a good estimator for constant additive treatment effects. So it's when you have constant treatment effects that are basically just kind of not changing across the population, and not a lot of outliers, right? So there's never anybody that has just some kind of extreme outcome. Everybody's kind of got some nicely distributed, maybe even like normally distributed outcomes. Okay. So let's calculate the test statistic. Let's see it in action. So what we're going to do is we're going to take the average here. And that average will be 34 over 4, right? So 34 over 4, let me do this with my calculator. 34 over 4 is 8.5. Okay. Then what we do is, oops. Oh, good. Okay, thank you. Oops. So that's the that is the average for the average outcome for the treatment group. Now let's take the average outcome for the control group. That's going to be average outcome for control group is, let me calculate that. That's going to be 30 divided by 4. $7.5. And just so we're on the same page, so that's 30 over 4. Okay. And then the simple difference in outcomes is here. It's just the difference between the two, and it's a 1. So notice what we get. Our step 2, our test statistic that we chose is the simple difference in outcomes, absolute value. And it is equal to a 1 using the original treatment assignment, right? All right. So let's now go through steps 3 and 5. What steps 3 and 5? Step 3 is the strangest step of all. In step 3, you will pretend to reassign the treatment. This is make believe. That's what we call it in the United States. Actually, I've never really thought about it, but make believe. We say to children when they are playing some game of imagination that they are playing make believe. It's all pretend. They're, you know, a child in the United States may pretend to be a superhero, right? He's not really a superhero. He's pretending. We are going to pretend to assign the treatment to different people using this, but the data won't change. Okay, the data won't change, but this actually is implied by the first step of the sharp null, as you will see, because the first step, our sharp null, implies that the original treatment assignment was irrelevant anyway. Because remember, the sharp null says there is no treatment effect, and so treatment assignment is irrelevant. So therefore, our pretend treatment assignments are just as valid as the real one. None of them should be producing treatment effects, right? So all you're doing under the sharp null is just comparing every single treatment assignment, none of which have any impact on outcomes, right? That's what you're doing. That's all you're doing. That's all you're doing. The original real treatment assignment is just as irrelevant as any of our make-believe ones. Any of our make-believe ones, right? So let's see. Let's see what we get. Right? So the key insight of steps 3 to 5, the null randomization distribution, is that randomization, this step is going to reassign in make-believe the treatment assignment for every combination. All right, so we're going to reassign it. We're then going to calculate a test statistic each time. That's going to allow us to get the distribution of counterfactual test statistics, and then we will calculate a p-value based on that entire distribution. All right. So the key insight is that the Fisher-Sharp null is that treatment assignments don't matter. Treatment assignments don't matter if there's never a treatment effect. Okay. But if there's never a treatment effect, then we can calculate p-values associated with the real one. How likely is it that the original test statistic came from the Fisher-Sharp null distribution? All right, because we'll have them. We'll have, under the Fisher-Sharp null distribution, every single possible conceivable test statistic. We'll have every single one of them. And we'll see how often it is that Fisher's sharp null distribution produces a number this large. Okay, so let's look at it. Then we'll get this p-value calculation. This, I sometimes hate notation, mathematical notation, because it takes so long to understand it. So let's do this one last. We'll come back to this one in a moment. Okay. All right, so let's look at it. This is going to be the first permutation. Now remember, originally, this was our treatment group. Okay, originally that was our treatment group. Ben was in the treatment group. But now look what we've done. We have pretended Ben was in the control group. Pretend Frank was in the treatment group, even though that isn't true. All right. But look what we're going to do when we do this. We're going to now calculate. Now we calculate new test statistics associated with this pretend treatment assignment. Okay. So it'll be based on it'll be based on this one, this one, this one, and this one. Okay, well, that average is going to be 36 over 4, not 34 over 4. That's a 9. Then we do the same thing here for the control group. And that'll be 28 over 4, which is 7. New test statistic from this pretend treatment assignment is 2, which is bigger than 1. And remember, to reject the null, the true treatment assignment must have a test statistic that is large compared to the Fisher test statistics. And already we see that this isn't true, right? 1, our true test statistic, is smaller, not larger than 2, our pretend one. Okay, so already we're seeing that, you know, under other treatment assignments, you would get larger test statistics. All right, so that's 1. Now we do another one. Okay, so we're going to leave Ben in the control group, but now we're going to put George in the treatment group. We go through, the 9 is the same because we're still using Andy, Chad, Daniel, George. Is that right? 10, 16, 3, and 8. Let me just double check that. 10, 16, 3, 8, divided by 4, 9.25. Sorry, I thought that was wrong. I need to update this. So this should be 9.25. And then let's calculate the control group. That's going to be 5 plus 5 plus 7 plus 10 divided by 4. That's a 6.75. All right, so 9.25 minus 6.75 should be 2.5. All right, so that the test statistic, the SDO test statistic for this, you know, this second permutation from the Fisher sharp null is 2.5, which is again larger than the one we find under the true assignment. So again, this is looking very different from what Bristol's case was. Remember, hers was large relative to others. These are small relative to a few. But let's see how many of the pretend test statistics are larger than the true, than 1, the true test statistic. All right, so we're going to do this. Over and over and over again. And when we do it, let's see if I show it here. Let's look at it real quick. So when we do it, I think I get it here. Yeah, we calculate the exact p-value. And when we do the exact p-value using R, right, here's what it looks like in Stata. Okay, I'm going to go through this technique in Stata. You can do it in R also. And when you do it, what I'm going to find, I'm going to show you what I find, and then I'm going to go back and show you how to do it. I actually find that that 1, what you will see when you code this in R, Stata or Python, what you will see when you code this in R, Stata, or Python is that around 60% of the time, you get numbers at least as large as 1 using pretend treatment assignments. So there really isn't anything all that special about the actual outcome we found. It could very easily have come from noise. Yeah, Alexander says, can we? No. So Alexander, you can well, Alexander, you can use Fisher-Sharp null anytime. Fisher-Sharp null is just based on data. Fisher-Sharp null is something that you can do under any binary treatment assignment. Doing it with continuous treatment assignments, that might be a little bit more challenging. I am not immediately positive how I would do that. That might be challenging. I think you can do it, but I don't know how to do it. But for binary treatments, you can do it. It's just that, you know, Fisher-Sharp null makes the most sense in the causal context, and it's in the causal context that we are focused on selection bias. So you can use randomization inference with experiments, but you can also use it with quasi experiments. You can use it with either. And either one of them is focused on addressing selection bias. So yes, you can use it. You can use it in situations where you are trying to eliminate selection bias. It's really a different kind of question than one we have for biases. It's about, once we have constructed our model that addresses selection bias, then can we construct p-values for that particular model? Sorry, I missed. How do you calculate the exact probability? Angelica, can you say that? Can you elaborate a little bit on that question? The lecture equal 1. Can you tell me a little bit more about? Can you say more about your?
Okay. What I want to ask is, you know how when we do the null hypothesis, we have to either reject or accept. Now, we have the critical value. Is that what we are talking about? Is 1 the critical values? The critical value?
Is 1 the critical value? I'm not sure if that is exactly the same concept. It is essentially, I think that might be the right way to think about it, Angelica. It's basically in the Fisher-Sharp null framework, the minimum level of the test statistics is the true one. So here it would be a 1. Here it would be a 1. In another context, it would be a different number. So it's not gonna, so it won't always be a 1. You use the true value as the minimum value of the test statistic that all other pretend test statistics must be less than.
Yeah. Okay.
So,
sorry, Prof. Is it the same, the concept of power of a test?
I think it might be the same as I think I'm not actually sure if it's exactly the same thing. This language isn't usually used with a lot of this. So I'm not exactly sure if it's exactly the same thing. I usually think of it in its own terms. I can I can answer that question, Angelica, and get back to you tomorrow. Let me do some research and see if people usually mean the same thing between this. I'm not exactly positive if it's exactly the same thing. What it's really going to be is it's going to be like this, though. We're going to get, under some kind of Fisher sharp, we're going to get some distribution. All right. And the true effect might be there. And our placebos are here. Okay. And all we're really trying to figure out is, well, what's the likelihood that this true one came from that distribution? Well, if it's far outside of it, then the probability that it came from that distribution is one out of, it's basically going to be, you're going to calculate a p-value that's basically equal to the rank of the true divided by the total number of test statistics. So if you have, this is the first, that's what this one would be. This one would be ranked first out of, say, 1,680. So this would be 1 out of 1,680. Might be, whatever that is. Or if it was 1 out of 70, let's say it was 1 out of 70, then that would be something like 0.014. All right. So I'm not exactly positive how these terms map onto each other. I really know it purely kind of in terms of itself, but I can find out a little bit more of how these two map onto each other. Is that, can I answer your question tomorrow, Angelica?
Yes, please, Prof. Thank you.
And Holger says, what was the value of the test statistic? Yeah, Holger, that's a great question. The lady tasting tea example was definitely a lot more difficult for me to express the test statistics, because it was really 0 or 1 based on the number she got right. So, hers was this was a purely combinatorics question, and I haven't been able to express in my own mind this in a SDO framework. So I'm not really sure. It was I think it's 100% associated with that particular choosing order. So it is a little more challenging to express than these simpler SDO or other estimator models, because Fisher wasn't estimating treatment effects. So test statistics were based on ordering. So it's a little, I find that it's interesting to talk about the history of the test statistic of the procedure, but I kind of prefer to go into the context of an experiment as quickly as possible, because those concepts of the test statistic don't really concern themselves with the order of the cups being chosen. And I find that that's really kind of hard. So I apologize, Holger, I don't actually know how to put into words a test statistic based on choosing things in a particular order. I just know that using that 8 choose 4 and that that particular expression of the combinatorics, you can get an exact p-value. And Angelica says, yes, Angelica, exactly. Fisher's test statistic doesn't follow a certain distribution. Or rather, Jessica, let me say it a little differently than that. Go back to that slide I gave here. Where is it? Here. The p-values, the inference that you're doing with Fisher's sharp null, it does not require making any assumption about any kind of sampling distribution, any kind of distribution of the errors. So you don't have to make, you're not making assumptions, you're not making structural parametric assumptions about any distribution. It's called exact. It's called exact. We call the p-values associated with Fisher's sharp null exact because they aren't based on a hypothesized distribution. They're actually based on calculating test statistics for every possible treatment assignment. There could be thousands, hundreds of thousands, even millions or billions possible treatment assignments in your data. Fisher imagines calculating all of them, all test statistics under every possible treatment assignment, and then comparing the true one with all of them in a simple rank-based p-value calculation. And if you can, because your computer is sophisticated enough, get all billion possible test statistics and do that ranking that I'll show now, you will have calculated the exact p-value, and it was never based on a distribution or never based on a hypothesized distribution. It was rather based on an actual distribution of test statistics. In fact, all test statistics possible. It's very different. It's very different. It's very different than what we're used to, than other types of inference, which is why I was a little hesitant to map it onto terms like power and critical values. I'm not exactly sure yet if those terms will carry over exactly the way they sound, the way they are defined, but I'll find out. I usually don't use them. So so we go through, okay, let's say that we had 10 test statistics and the true one was larger than all Fisher-based 10 test statistics. Our exact p-value would be 1 over 10 or 0.10. That's all a Fisher-based exact p-value is. It's the ranking of the true test statistic, ordered ranking against all other Fisher test statistics, none of which are real. Okay. All right. So that's why we need the true value to be relatively large, because the final exact p-value is based on an ordered ranking. An ordered ranking of those test statistics. Only the larger test statistics are at the higher rankings. And unless you have a large enough test statistic against the distribution of the Fisher test statistics, you can't reject the null at some reasonable level of confidence, like 5%. All right. So what are some alternatives? So this example was using the simple difference in outcomes, which Embens and Rubin said was best for constant treatment effects, constant treatment effects with very few to no outliers. But what if we have outliers or heterogeneous treatment effects? Then STO isn't probably the best one, because it is so deeply influenced by outliers, because it is calculating means. All right. So we need test statistics then that are less influenced by outliers. We will look at a few. Now, logs, quantiles, and a rank-based one, and one based on distributions called the I can't remember how to pronounce it. Karamazov-Smirnov test, the KS test. So let's look at all of those. Let's look at all of those now. So there's transformations you can do that are less influenced by outliers. One is the natural log. Okay, so I say here, if you have a constant multiplicative effect, you might want to use the log transformation. Or if you just found a lot of outliers in the data, you might want to use the log transformation. This is useful for skewed distribution of outcomes. Okay, so you'd have to evaluate your data and decide whether or not you thought there was, calculate the degree of skewness, and that might cause you to move into a log transformation. But notice, it's still just the average of the logs, the average difference in the logs. You could also use quantiles. Quantiles are going to be extremely invariant to those outliers. Okay, so you'll that might be something you do again, is use a median, a difference in the median. Could you use rank test statistics? I have colleagues that love these rank test statistics. I don't have a particularly strong attachment to any of these test statistics, because I usually use regression-based test statistics for mine. But the basic idea of the rank test statistic is to rank the outcome. Higher values of Y will be assigned higher ranks, and then calculate test statistics based on the rank. This should not be confused with the way that we calculate p-values based off ranks. This is transforming the outcome. This is based on the test statistic. All right, so let's look at this. So let me just show you here. Oh man, I still keep forgetting to do this. This is incorrect for here. This should be a 2. So let me just. I've got to change this. I keep forgetting to change this. So let's look at this. So what I'm going to do is I'm going to go through a series of steps. The rank test statistic will transform my Y outcome into a new outcome called R. And R is a normalized ranking of the Y itself. All right, so watch what I'm going to do. What I'm going to do is I'm going to see how often a unit's outcome is larger than its competitor, than others, and count the number of times, including ties, that it is. All right. The more times that a unit's outcome is larger than others, we will count it with an integer, right? And when it ties, it will get 0.5. The more times it is larger the rank, then we will normalize. All right, so let's do that now. Okay, so what we'll do is let's look at Andy. All right, Andy has a 10. Andy has an outcome of 10. Okay, so what we do is usually we say we start with a 1 for him, then we add a 1 every time he is larger than someone else, and we add 0.5 if he ties. So he is larger than Ben, Daniel, Edith, Frank, George. So that's 1 plus 5 equals 6, and he ties with Hank plus 0.5. So his rank is 6.5. Okay, we will look at R in a minute. All right, so I do that for Andy. Now I'll do it for Ben. Ben starts with a 1. He is only larger than Daniel plus 1, and then he ties with Edith, 0.5. Okay, so that gives him a 2.5. We do this for everyone, and we get that second to last column labeled rank, right? So we get this column right here based on that transformation, right? Now what we're going to do is we're going to normalize. We now normalize, right? We now normalize using the normalization method that we're going to use is right here. Calculate the absolute difference in absolute ranks. Normalize the ranks to have mean 0. So what we're going to do is we're going to take its rank and we're going to subtract out n plus 1 over 2. All right, so n plus 1 over 2 is 8 plus, so it's going to be 6.5 minus 10 over, what was it again? Sorry, for some reason I'm drawing a blank here. N plus 1, sorry. In plus 1 over 2. All right, so I messed up. So in plus 1 over 2, so that's going to be 6.5 minus 11 point, so that's 11, hold on. Is that right? I think it's gonna go, let me see, I think I'm doing something wrong. Hold on. For some reason, I drawing a little bit of a blank. Oh, let's see. So I'd say number of times it's less than minus n plus 1 over 2. N is 8. Oh, I'm sorry, it's an 8, not a 9. So I go 6.5 minus 8 plus 1 over 2, which is 6.5 minus 9 over 2, which is, yeah, so that's 6.5 minus 4.5, which is 2. All right, so that's what I did. So I got a 2 for that one. I'm going to get a negative 2 for this one. All right, so what this is doing right here is this is ensuring, and this I said I did wrong. This should be negative 2. So what I've got here is mean of 0. So it's a normalized rank. But notice the spread is a lot smaller. So the influence of these outliers has shrunk as a result of this transformation. And now we use only the 6th column for our test statistic, R. We are not going to use Y to calculate three to 5, again, to calculate exact p-values. This will be more robust to large fluctuating outliers in our data by reducing their ability to influence the outcome, the final p-value calculation. Now that's all based on average differences between groups. There's one though that's based on the difference in the distribution of outcomes. It's called the Kolmogorov-Smirnov test statistic. And what the Kolmogorov-Smirnov test statistic does is it looks at the distribution of Y across the sample for the treatment group and the control group. And then it compares that distribution, that empirical CDF, and then it calculates the largest difference between the two groups. So let me show you what I mean. So here's the density. This is just the distribution of the outcomes for the treatment group and the control group, from which we get an empirical CDF. Right, so this is just the cumulative density function based on this frequency of the distribution of the control and treatment group. And notice at different points, you've got the differences here. But notice they're getting smaller. Notice they're getting smaller here. Get really small. But the biggest they ever get right here. Okay, that's the largest it ever gets. The largest gap between the two groups' respective CDF is that last vertical bar. What is this vertical bar? Notice it is a number. Looks like it's about 1 minus 0.59. It's around 0.41, right? The vertical bar is our test statistic. Remember, all we need for Fisher's sharp null is a number scalar based on D and Y. And KS goes through a series of steps that allows us to calculate a number. We will then reassign the treatment repeatedly through steps 3 to 5 and get a distribution of those vertical lines. That distribution will allow us to calculate exact p-values. Exact p-values. So when I do that for Rebecca's data, actually turns out that Rebecca's data, it is very unlikely that that data came from the Fisher distribution. Now the problem is the number of combinations. So let me show you. Let me just show you here. What's it called? Wolfram alpha. So let's do this. Let's do 4, choose 2. Right? 4, choose 2. There are 6 possible combinations. Oh no, sorry, this isn't showing me what I want. I'm gonna do it here. I'm gonna do 6, choose. I'm gonna do 6, choose 3. 20 possible assignments. Right? So for 6 units and 3 treatment groups, there are 20 possible treatment assignments. So your computer only has to go through 20 different assignments to calculate that, that distribution of test statistics. Because remember, Fisher is actually constructing new variables and repeating the analysis over and over. That's why it seems like bootstrapping, even though it isn't. Okay. But for 6 units and 3 treatments, it will be fast because there are only 20 possible treatment assignments associated with that. This was the lady tasting tea. Remember, there was 70. So 70 treatment assignments. It's getting bigger. What about 10, choose 5? Okay, it's getting a lot bigger, a lot faster. 252. Your computer will handle that just fine. Okay, 924 treatment assignments. What about in Rebecca's study? 2,000 units, 800 treatment assignments, undefined. If I go to Wolfram Alpha, see if I get anything there. That's how many different treatment assignments there are. Okay. So even with really modest numbers of units, you can't calculate exact p-values. That's where I'm going with this. So basically, even though Fisher provides a method for calculating exact p-values, you probably can't do it in your data, because in the 1930s, Fisher experiments were small. You could do this by hand. today, experiments or data sets have thousands of observations. Your computer can't probably calculate exact p-values because the number of treatment assignments is astronomically large. So what do we do? Okay, Sasha must leave. So let me wrap this up. So what you can do is you can use simulation. And what you'll do with simulation is you'll essentially just randomly do the assignment up for thousands and thousands of times, but not necessarily every iteration. And when we do that for Rebecca's data, when I do 100 trials, Rebecca has the largest iteration. When I do 500, she still has the largest. 1 out of 500, 1 out of 1,000. And what Embens and Rubin show is that it converges to that true assignment, that true p-value pretty quickly. You can also include covariates. You can run a regression. So in conclusion, the ability to do randomization inference is nice because it doesn't make distributional assumptions about the data. And what it does is sometimes the distributional assumptions that we've been working with are based on hypothesized sampling distributions, which may not really be realistic in your data. So you have these alternative hypotheses that you can, these alternative nulls that you can work with that are possible, okay? So tomorrow I will be here on time. I apologize, this won't happen again. Tomorrow what we will do is we will dive into non-experimental methods for doing causal inference. We'll do regression discontinuity tomorrow. On Wednesday, we'll do instrumental variables. And on Thursday and Friday, we will do difference in differences and synthetic control. So I encourage you to